So I can do this the other way too. I can measure how high a projectile goes and use that information to measure, to calculate, to predict how fast it was initially going. So again, I'm using kind of a silly example here where I'm on the moon just to show what this looks like for a different acceleration. But more practically, if you're a person who likes model rockets, you can use this kind of mathematics to know how fast your model rockets go. All you need is, say, a sextant, so you can look up in the sky and you know how high your rocket went. And then using that information, we can build a function that'll tell us how fast it was going. So this situation, I have actually made it to the moon, and I snuck a football up on the spaceship with me. I throw this football up, and it goes exactly 100 meters before it starts to fall again. So yes, again, I'm using some sort of device to measure distance up. Well, not up in the air, but you know what I mean. And I'm going to use this information along with having an approximation for the force of moon gravity in order to figure out how fast I threw that football. So I know I want this height function I know that that means I should have its derivative. And I should have its second derivative as well. And it's the nature of these kinds of problems that it's the second derivative that I know. And the other two I need to find out. Well, my velocity function, my h prime, is supposed to be the antiderivative of the second derivative. So this should be negative 1.6 times t plus some constant. What is that constant? Right? Like literally, what is it? For right now, it's just some number that I'm calling c. This constant is exactly h prime of 0, the initial velocity. Why am I making a big deal out of it? That's the number I actually want to solve for. So the very last thing I do in this problem is going to be solving for this constant. Let me go ahead and give that a special name. I'll call that v for initial velocity. What does my original function look like? It's going to be negative 1.6 all divided by 2. Let me call that negative 0.8 times t squared plus v times t plus what? Some constant, right? My constant here is going to be my initial position. And again, the problem does not specify otherwise, so I'm going to presume that this football must have started on the ground with a height of 0. So I still don't know what this initial velocity was. However, I know that this position function, this height function, is a quadratic. And I know what quadratics look like. I have some downwards facing parabola, and I know its maximum value. Right? Goes up exactly 100 meters, then starts to fall again. So let me work out a little bit. My global maximum, again, I know that this is the global maximum because I'm working with a downwards facing parabola, is y equals 100. Okay? Where does that maximum happen? This happens exactly at my critical value. So this happens at x coordinate. What x coordinate makes the derivative equal to 0? That'll be my velocity number, a number that I don't know, divided by 1.6. So if x, excuse me, t is equal to that. I'm not following my notes here. T is equal to velocity divided by 1.6. Okay. So again, velocity is a number I don't know here. But I do know, if I knew that velocity, where the global maximum should be. Well, let's plug this value of t into the original function, see what we get. So my maximum is supposed to be at t coordinate v divided by 1.6. And this is supposed to be exactly 100. So what have I got here? I'm supposed to have negative 0.8 times t squared. What number is t squared? That is v squared divided by 1.6, which is squared. And then I add to this v times t, so that would be v squared divided by 1.6. That's kind of funny. Let me write this out to show the division a little bit better. So I've got negative 1.6 divided by 2. I'm just unpacking that 0.8 there. V squared divided by 1.6 squared. Okay, keep going. And this is plus v squared divided by 1.6. All of that is equal to 100. Well, I can cancel on this fraction a little bit. I should be getting v squared divided by 1.6. And let's say this is all times negative 1/2. And then I need to add to this v squared divided by 1.6. I have a number I would like to solve for. There it is again. So if I'm taking negative 1/2 of something and adding it to itself, that should just be 1/2 of v squared on 1.6. And oh, sorry, this exponent right here is extraneous. I apologize for that. So this one is multiplying, that's a decimal. Maybe I'll call that v squared divided by 3.2. That looks pretty good. V squared is, v squared divided by 3.2 is 100. I like that a lot. That's the number that I want in an equation that's not too bad. So what am I going to do? I'll multiply both sides by 3.2. $320 has to be equal to v squared. So v should be the square root of that number. And I'm basically done at this point. Just for fun, let's say this is, how many things can I factor out of here? 32 and 10. So that would be 64 times 5. I know that 64 is 8 squared, but the square root of 5 is irrational. So my velocity is I've got 8 square root of 5 meters per second. That's my answer. Or if you would like a decimal expansion, that's fair. What is the square root of 320? 17 point, let's round up, so call it 17.9. So, just to recap, knowing my model, knowing acceleration on the moon, knowing how far up my football goes before it starts to fall again, these things together allow me to determine what the initial velocity was. I start with the function that I know. It's not the function that I want, it's just the function that I know, in this case, the second derivative. I'm going to take an antiderivative. And this problem was a little bit more advanced because I wasn't able to directly find out the number that I wanted. I needed to puzzle it out a little bit more. So taking another antiderivative, I get back my height function where I know I've got extra information. So I've got information about the second derivative. I've got information about the original function, and I'm going to use those to leverage and figure out what my derivative has to be, coming at it from both sides here. Now I know what parabolas look like. I know where they have maximums and minimums. So I know where my critical value is going to be, even if I don't know what number v is exactly. And knowing the y coordinate of the maximum, together with the t coordinate of the maximum, gives me this nice equation. I solve for the quantity that I wanted. I solve for my initial velocity. So what's the payoff? The payoff is if you know how high an object got before it starts to fall again, thanks to calculus, we can figure out its initial velocity. What was its speed the very moment it got launched up into the air?